Hey everyone. So up to this point, we've been talking about vectors and what vectors look like and how you can use them and different ways to combine and transform vectors. And all that's well and good. Today, what we're going to talk about in 6.3 is what we're going to do is shift away a bit from the whole idea of vectors and talk about something that you've heard once or twice before, but we've never really gone really deep into. We're going to talk about parametric equations. And I'm really glad I get to be the guy who gets to share this with you because parametric equations are really, really cool. They do really, really fascinating and powerful things. It kind of changes the way we see graphs. And I want to share this with you. And it seems, I think you'll really like it. But that's a big wind up. Let's see if I can actually deliver. Here's what parametric equations are all about. I think parametric equations really came out of a problem. And here was the problem that we had. Whenever you make a graph, let's say we wanted to try to graph something, and let's say we're going to graph, say, how much money we have over time, or how well the stock market is doing over time, any of those things. And so you could make this graph that goes up and down and up and down and so on. And you can say that at the bottom we have time. And so we're graphing, we have our x-axis. Our x-axis will be our time axis. And for y, we'll say that's how much money we have. How many buckets of money we have. And that's all well and good. So you can read as you go further right, if you went to any specific time, so maybe this is year 2000, and this is year 2016, you can kind of see how much money you have over those different time periods. And and sure, it works. It does the function. It does what we need to do. But time seems to be a little bit different than just a left to right graph. I mean, we have a whole timelines and things like that. We have timelines that go from left to right, but it seems like time can be represented a little bit better because isn't time really just a thing that happens in an experience? And so one of the things that we said, well, why do we have to limit it to just left and right? Why can't we let time express itself in a way that time always expresses itself over time? So why can't we say, for example, if I wanted to graph, for example, the movement of a ball across a table, I could say the ball moves like this across the table, right? And why can't I just make a graph that graphs that movement of a ball across the table? And then I can say as time progresses, I can actually watch the ball move across the table. So it starts over here, maybe over here, and then it starts moving. And you can see as time progresses, you can actually watch the ball move. And that's the idea of what a parametric equation is. It says we'll actually incorporate time, the actual element of time as we experience time, this thing that keeps moving forward. And we can actually watch a graph move and change and grow. And it's cool. We can watch time move and change and move things. So with our money, we can watch the money go up and down. We can actually watch that happen. And that's the fundamental idea of a parametric equation. It says let's redefine things. Let's redefine things so that we can actually use time like time. And so we can watch things move like time. When it comes to an actual equation, the 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 idea of time kind of gets split up into two separate different equations. We need to have an equation for that represents how high things are and how far left and right things are. And so when we make a parametric equation, we actually split it up into two completely separate equations. Here's what I mean. We have one equation, say y, that defines things in terms of time. So we can say that like y equals, I don't know, 2t. So that, let's say 2t plus 5. Let's make t a little bit clearer. This is our fancy curly t. So as time progresses, we can see exactly what y value we'll have. And our x can be, let's say, I don't know, 3t plus 2. And so what it's saying here is that we're going to start off with a graph, and when t equals 0, we can actually, if we were to plug in like 0 for t, we could figure out what our x and y coordinates are, where we're starting. So let's say t equals 0. If t equals 0, we would plug in 0 for x and y, and we'd get y equals 2 times 0, 0, plus 5, and x equals 3 times 0 plus 5. And you can see with this, plus 2. And so that would work out to be y equals 5 and x equals 2. And so when you want to graph an equation like that, we would actually just graph those points. We would say x is 2 and y is 5. So we would graph in the very beginning, if I did that correctly, I think that's correct, yeah. We'd graph this little point here, the point 2, 5. And so if you wanted to graph the next point in time, as time moves, as you went to seconds, so that's the first second, time at t equals 1, you'd plug in 1 for t, and you'd plot that point. So we'd say, let's see, that'd be, if we plug in t equals 1, so if we got the first element of time, we did t equals 1, so that'd be y equals 2 times 1 plus 5, and x equals 3 times 1 plus 5, or plus 2, excuse me. So y would equal 7, and x would equal 5. So at the second point, we'd get 1, 2, 3, 4, 5. Let's see. And we'd plot a point right about here. And you can start to see that it'll move. Maybe it'll move in a line, maybe it'll move it in a curve. We can kind of see as we plot more points. And so you can kind of see, like, as we plot more t, we can get more of a graph. And you might be saying, well, Mr. Jurashek, that's all well and good, but we're just plotting a line here. We could always plot a line. And we could maybe delineate by saying, like, we could always plot a line with a certain slope or whatever, and we can go from x is equal to 0 to x is equal to 5. In this case, x, we could say our boundaries are 2 is less than or equal to x, is less than or equal to, what is that, 5? And we could plot the same thing. And well, sure, for most cases, for many cases that works, especially when it's a function. But sometimes, one of the cool things about parametric equations is that you can graph anything, absolutely anything. When we think of a graph, normally, we think of a line, we think of maybe a curve or something like that, or maybe a U, maybe like maybe a parabolic thing. It's a parabolic is different from parametric. We draw a parabolic U, and you could draw things like that, but you couldn't draw. It'd be much harder to draw, say, a circle, or maybe just any drawing. Like the parametric equation lets you make a circle super easy. It lets you make this little thing really easy. It's basically the Etch-a-Sketch of the graphing world, and it's amazing. So, and here's a good example of it. So, let's say you could actually graph this right here. This I guess this is Applejack. You could graph this. This is a graph. This isn't a drawing, which you see here on the right. This is actually a graph of a plot. Now, granted, this is a very, very complex graph. This is extremely complex. I mean, if you want to see the graph, it looks like this. This is x equals all of this, all of that, and y equals all of this. So if you were to plug all this into your calculator, everything there, and press the graph button, you'd actually be able to graph this on your calculator. And so it's fabulous. It's fabulous. But I don't think, if you manage to do that, let me know. I mean, I'd love to frame it or something. The fact you put all that into your calculator, man. Normally it's better to just use a computer calculator, you know. But that's the idea. You can graph literally anything. And let's see a little bit what that looks. We're gonna look in a second or what that looks like. But before we get into that, let's kind of, let me make some space. I want to just kind of give you a general idea of, well, sometimes things come in a parametric form, and you want to work with it in a really simple, easy, non-parametric form. You want to just turn it back into what it's used to be, a function, and we can do that. We can change things back into function pretty easily. Here's what I'm talking about. So that was the first idea. What is parametric? The second idea is sometimes we need to take these parameters that are made and kind of eliminate them to make it back into a function so we can understand it a little better and use it how we'd like. So let's say we have a really cool parametric equation that says y equals, I don't know, 2x plus, not even 2x, that's not parametric. We want to say 2t plus 4, and we'd have x equals, let's say t divided by 3. Okay, if you wanted to bring this, you can take many things that are actually functions, or even things that aren't really quite functions. You could do things. You can manipulate this to actually turn it back into that function notation we're used to. It won't work as well, and you might. And if you want, I wish I'd love to talk to you more about why that is. But unfortunately, we don't have time. But to solve a problem, we can actually take a parametric equation and turn it back into a function. Here's how we do it. First, we'll take the x side, or it doesn't really matter which side we take, but the simplest way is to start with the x bit over here, and we will solve for t. So we'll solve for t, and you might be able to see intuitively what that is pretty quickly. So 3x equals t. That'd be the solution for if you're trying to solve for t. And now we know that t equals 3x. You know what the equal sign means? It means it's the exact same thing. So we know that 3x and t are the exact same thing, so we can substitute in 3x every time we see t. So if we look at this top equation, y equals 2t plus 4, we can substitute in 3x for t. We could say y equals 2 times 3x plus 4. And then reduce it down, so then y equals 6x plus 4. And so if you were to graph these two equations, because it happens to be a function, what you're graphing, you could graph y equals 6x plus 4, and that would look the same as this parametric equation here. And assuming, of course, that you graph all of t. If you plug in all the values from t, from negative 100 to 100 to negative infinity to infinity, if you graph in all the numbers, you will get the same equation. It'll look exactly the same as y equals 6x plus 4. Okay, that's the idea of eliminating the parameter. Now let's actually get into the nitty-gritty of how do we do this? How do we make these graphs? How do we work with them? And so forth. Well, we're going to work with a little bit, a new part of our calculator that we haven't really talked about so much. We've talked about a little bit before we got out. But this is this function, this idea of graphing with parametric equations requires a whole new function on our calculator. So if I pull the calculator out, that's a new way of pulling calculators out. It's pretty cool. I want to let you know that if you're using the calculator that I've always been recommending, GCalc GCalc. There's another one called like Calculator X84 if you're on Android, something like that. The parametric button will not work. You actually need to go beyond a paywall in order to do it. It costs like $5. If you need to get it, I've tried to find a way around that. I tried to find other apps that would do this that would do the parametric function without this, without you having to pay any money. And there is one on iOS that will work if you that might work if you do something, if you go into the beta program and all of that. So if you're really interested in saving $5, let me know. I might be able to help you out. But for those of you who do have the full app, the Pro app, you want to go into Mode, press the Mode button, and then you'll see a bunch of different options. This is the same for your TI-84 calculator, assuming you have your TI-84 with you. You can choose for the Y variable. You should have a bunch of different options. Func for funky, par for average, pol, and seek, or more accurately, func for function, p for parametric, pol for polar, and seek for sequential. We're going to go to par for parametric. And you'll notice when you go into parametric mode, it changes the way your calculator works. So if you go to y equals, well, let me clear that. That was from earlier. If you go to y equals, now you no longer have just y1, y2, y3, y4. You have x in terms of t and y in terms of t. So now it gives you those two lines. You can actually graph any parametric equation. And you'll also notice that if you want to plug in your variables, if you want to plug in x, you no longer, if you press the x button, x won't go out. T will go out. So for example, if I want to graph the equation y equals 3t plus 7, as I plug in that t, as I press the x button now, because it's in parametric, it's going to press t instead. Now, and if I plugged in, let's say x was, I don't know, let's say t times 2. Okay? And when we graph that, we will see the graph. We'll see, we can actually graph the same thing. So the graph looks generally different. If you try to do some tracing, you'll notice that at the top, it'll give you not only what x equals and y equals, if you do trace, yeah, but it'll also give you a t equals as well, because it gives you what time we're currently in, how many seconds have elapsed, or whatever unit of time we're using has elapsed. Cool. So that's the basic idea of how to use the graphing calculators. So there's a little bit more, but we'll get to that later. Yes, so that's how you get into the parametric mode. It'll be very useful when you actually get into the problems. Let's talk about now how to actually make parametric functions. And this is the fun part. Let's say we have a whole function and we want to make it parametric. Some easy ways to do that. Let's say we had, for example, y equals 2x plus 7. Let's say we wanted to make that parametric. Well, a really, really easy way to make a parametric equation out of that is just to replace x with t. So instead of saying y equals 2x plus 7, we will now have y equals 2t plus 7. And for x, we'll just say x equals t. Yeah. And that's what you have it. So if you graphed y equals 2x plus 7, and then this parametric equation below, those will both graph to the same thing, assuming you graph all of t. Oh, I'm sorry. One more thing about the graphing calculator. Before, you may be a bit familiar with this window button, about how you can choose maximums and minimums for what you can see on the screen. So normally you would be able to say set like an x-min and x-max, which shows you how far left and how far right are on this. You'll see the screen, and then a y-min and a y-max, which shows you how far up and down you can see on the screen. But if you plug in now what you have another option now of t-min and t-max, which lets you see how many seconds are graphed. So we'll start from we can start from 0 seconds and graph up to 3 seconds. And so when you actually look at the graph, it'll actually only graph those first 3 seconds, as you can see. So 1, 2, and 3. So those are the 3 seconds it graphs. And so you'll want to make sure when you're graphing a parametric equation that you actually encompass all of t that you want to encompass, because it is like its own variable. It's time. Instead of going left and right or up and down, you're going through time, forward and backward in time. So that's a bit of what it is. We'll get into a little bit more of what that looks like, what time looks like in a second. Let's secondly talk about the algebra behind making a graph if you're given 2 points. Let's say you're given the points 2, 3, and 4, 5. I just want to first quickly give you the equation of this, the equation of the parametric, how to make a parametric equation, the standard form, and then I'll show you kind of what this looks like. In a few seconds, I'll be able to show you exactly why this works the way it works. So, x, if you have 2 equations, let's say point 1 and point 2, then you'll take that x should equal x1 plus t times x2 minus x1, and y should be y1 plus t times y2 minus y1. Excuse me. So when you graph this, so if you had 2, 3, and 4, 5 as your 2 points, then your equation would be x equals 2 plus t times 4 minus 2, and y equals 3 plus t times 5 minus 3. So that'd be, and so this parametric equation would look exactly like the line that goes between these 2 points. That's what I'm trying to say here. Okay. Now let's say you wanted to graph a line segment, and this makes it a really easy way to graph a line segment. If you start with t equals 0, you'll graph the first point. If you plug in t equals 1, you'll graph the second point. Let me show you how. So if I plug in, if we look at this equation that we just made here, this equation here, and we said t equals 0, what point would that come out to be? Well, that'd be x equals 2 times 0, or 2 plus 0 times 4 minus 2, and y equals 3 plus 0 times 5 minus 3. And let's see, the zeros, these just cancel out whatever's next to them because we're multiplying against all that. So x equals 2 and y equals 3. Our first point, so our coordinate would be 2, 3. And that, you might be able to see why that makes sense, because our equation, on the left side we have x equals x1, it starts with x1, and it starts with y1. So this x1 and y1, that's really our starting point of the equation. That's cool. Now, let's say we plugged in 1. If we plugged in 1, let's say that, let's go ahead and do that. If I plugged in t equals 1, instead of having what you might be used to, instead of just having the actual points, we'll actually get something a little bit beyond those points. We'll get 2 plus 1 times 4 minus 2, and we'll get 2 plus 1 times 5 minus 3. And so we're at, oh sorry, not 2, we'll get 3 time plus 1 times 5 minus 3. And so you might be able to see kind of what we were doing here from our starting point 2, as far as y goes. Sorry, as far as x goes, we start from 2, and now we're going to add whatever the difference between 4 and 2. We're going to add the difference between the second point and the first point. So we're going to do whatever we need to, essentially what it's saying is, we're going to start with 2, and we're going to add whatever we need to add to get to that fourth point, to get to that 4. Or in other words, get to that second point, excuse me. So we're going to start with 2, we're going to add whatever we need to add to get to the second point. For y, it says we're going to start with 3, and we're going to add the difference between 5 and 3, whatever we need to add to get to the second point, or to get to 5. And so when you graph this out, or when you calculate this out, this will be 2 plus, let's see, 4 minus 2 would be 2, x equals 2, and y equals, let's say, 3 plus, let's see, 5 minus 3 is 2, and so we will add, so x will equal 4, and y will equal 3. No, not 3, it will equal 5. Good. And so our point when t equals 1 is 4, 5. Cool. So that's the second point. That's the second point. And if you want to, I encourage you to really get this into your head and see why it does this, why it's doing this. Another way to think about it is that difference is kind of like its slope, where we're kind of going up the required amount every increment. Well, it is pretty much its slope. We're going up the required amount we need to go up every time in order to get to those points. So that the second bit kind of helps us find the slope. Okay. But really all you need to remember, that was just some extra stuff, but all you really need to remember is that if you're from t equals 0 to t equals 1, you can, if you set your boundaries as, let's say if we set our boundaries as 0 is less than or equal to t is less than or equal to 1, then that'll just graph the line segment from one point to the next. Okay, I feel like before I go to the next one, I feel like we've got a lot in our head right now. I'm gonna try to let's go over and go to Desmos so we can kind of see how this all works out. Let's start with the first one, the 2x plus 7, right? So what I've done on the left side, this is the graph. This is the way a Desmos reads a parametric equation, where it says we're going to graph a point, or graph a line segment in a sense, where the x equals t and the y equals 2t plus 7. So you can see that's the same thing as our previous one. Y equals 2t plus 7. X equals t. That's the first one up here. Okay. So if we go back to Desmos, we will see if I want to graph this equation. Let's see. I've graphed from t equals 0 to t equals b, and I've got this b slider on the side, so I can kind of see what's going on. Let's say if I want to make b a little bit bigger, I can start. So we start from that 7, and as I start graphing more and more of t, you'll see that the line gets larger and larger and larger. And so that's kind of the idea of what parametric is doing. As we graph more and more of an equation, we'll get this, as we graph more and more of t, we'll see the actual point progress and move and change. And so we can kind of watch that progression, watch that movement as t moves forward. So that's the idea of what that line is. Now let's kind of graph that second point. We made a parametric equation off of 2 points, 2, 3, and 4, 5. So if I'm right, if I'm not speaking total, if I'm not leading you astray, I should be, when we graph 0 is less than or equal to t is less than or equal to 1, if we graph from 0 to 1, we'll get a line segment from the first point to the second point, 2, 3 to 4, 5. And you can see, When t equals 0, when it's just 0, it goes from 0 to 0, then there's not really, let's zoom in to the point that we're looking for. There's not much you can see. Let's see, it kind of starts off at that 2, 2, 3, the point 2, 3, which is our first coordinate. That's our first coordinate. And if we graph all the way to 1, let's see if I get exactly 1, there it is, we have a line segment now. So we go from, what this graph is saying is we go from 0 is less than t, which is less than or equal to t, which is less than or equal to 1. That's what that middle, on the left side, that's our parameters, because I went from 0 to t to b, and b is 1. But what we're saying is that this is now, but now what we can see is that what this creates is a line segment that goes from the first point to the second point. You remember why that is, because if I plugged in 0 for t, I would get the first point. Plugged in 1 for t, you get the second point. So, or if we're going all the lines, all the points between that first one and the second one, we're going to graph the line segment between them. Anyway, if that was a little bit too confusing, don't worry about it. It's fine. It's not vital to know. The third one is a circle. I told you we can graph circles with this really well, and we can. Here's the formula for it. Let's say we want to have it with a radius of r and we want to have a radius of r, and we wanted to graph t% of it, or we want to graph a certain number of radians. We would say x becomes r times the cosine of t, the number of radians we want to graph, and y is r times the sine of t. And here's what this is saying. It's saying that we're going to start with, for the x value, we're going to graph the cosine of our angle. So let's kind of think of t as maybe the angle we want to graph, or yeah, maybe an angle would be helpful. Then you remember that cosine, the idea of cosine, the meaning of cosine is the x value on the unit circle. And sine is the y value on the unit circle. What cosine and sine graph are the x values and the y values of a particular angle on the unit circle. And so if we would graph that and then multiply it by its radius, it'll be that point, that x point and that y point, the x coordinate and the y coordinate on the unit circle, scaled up or scaled down to its radius. That's all a lot of mumbo jumbo. Let's kind of see what this means. So let's get rid of this graph and move to this one down here. I want to make our radius 5. Okay, well, that's 5. Here we're good. So you can see, as I graph more and more of t, I graph more and more of the circle, of a circle. This is about pi. Yeah, it's about 3.13. It's about pi. If I graph all the way to 2, that gets me, or 2 pi, that gets me the whole circle. And so I can, by how much t I graph, will show me exactly how much I'm graphing. I can actually let that just go on its own. And so you can watch it graph. You can watch time move forward, and it graph a certain amount of it at a certain time. Another thing I want you to notice about this is that after we've crossed 2 pi, you can see the slider is still moving. It's still graphing even more, but it's graphing over top of itself. You'll often see this when you graph a circle. If you graph more than 2 pi of a circle, you'll keep going in over and over and over and over on yourself, and it won't actually look like anything additional is being graphed, because you're just drawing a line on top of your line. And so that's what's happening here. That's why it seems to stop at about halfway through, because you graph the whole circle. It's just tracing over the exact same line again. Now let's see. So while that's graphing, I can change the radius of any points. It's how much. If this was just 1, it would just graph the unit circle. As you graph more of it, because we're graphing the sine. The y coordinate is the sine of it, a sine of the angle, and the x coordinate is the cosine of the angle. So we're just graphing literally the unit circle. But if I change the multiplier, that radius, I can choose exactly how big I want to make that circle. And so that's kind of what's going on here. I'm choosing exactly how much I want to make that circle by the radius. And that radius is kind of the multiplier we use to graph different sizes. Okay, I hope that's not completely confusing. I hope it's a little bit cool. I think it's really, really cool. But let's get back to this. Let's say you wanted to get to, yeah, so that's really all there is for the actual lesson bit. There's a little bit more we can look at too. Like for example, we're going to talk about, there's a little bit of something to know over here. When we get to a problem that involves minimums and maximums, we're going to look at this specifically and figure out how do you graph a minimum and maximum on your calculator. It works the exact same way as before, but if you're using a calculator app instead of your normal TI-84, there's a special way to do it. And so I wanted to introduce you to that. You could use this method too. Anyway, if you're using a TI-84, but TI-84s have some pretty powerful and quick ways of graphing it up that are much simpler than that method right there. Anyway, let's move on to the actual problems then, and kind of figure out how to apply this in the actual problems, problem by problem. Okay, the first one says use an algebraic method to eliminate the parameter and identify the graph of the parametric curve. Use a grapher to support your answer. So immediately I try to take everything a chunk at a time and kind of like a clause. If you think about English, you think about it like an independent clause at a time, or maybe even just a dependent clause at a time. Clause by clause, what's going on. And so the first clause says, use an algebraic method to eliminate the parameter. So that's one thing we need to do. And the next thing it says, and identify the graph of the parametric curve. So that seems like the second thing we need to do. And finally, use a grapher to support your answer. So we're going to end up graphing this at the very end. Cool. So we're going to eliminate this parameter. It says we have this parameter and we want to get rid of it. So remember the steps that we have. We start with, we have y equals t and x equals 1 plus t. Now remember the steps we had that we covered right up here. If you want to eliminate a parameter, you solve for t on the x equation and you plug in your answer to the y side. Okay. If you're having trouble doing this on your own, look at this. See, here's what we're doing. So we're going to solve for t on the x equation. So we'll do, let's see, solving for t, we'll subtract 1 from both sides. So we get t equals x minus 1. Cool? Now we know t equals x minus 1. So we can actually graph that exact, we actually plug in x minus 1 for t on the y equation, because t equals x minus 1. So instead of writing t in the y equation, we'll write y equals x minus 1. And that is our new equation. This has eliminated the parameter. This is step 1. This is step 1. Done. Okay. Cool. Now we have to identify the graph of the parametric curve. We have to figure out, what does this look like? What does this look like? And so now that we've got it in something that's a little bit easier, well, it's something we're more familiar with. Now it's in that in a normal function looking equation, we can kind of tell, well, what is it? This one actually looks like, well, if you're familiar with slope-intercept form, this looks like the equation of a line in slope-intercept form. So y equals x minus 1. It looks like a line. And here's some other options you could have. It could look like, if it looked like a circle, for example, you'd have something like x squared plus y squared equals the radius squared. That's the circle, remember? And then a line would be y equals mx plus b, would be a line. And other forms like that, if you had like y equals x squared plus b, then that would be a parabola. The different kind of things you can remember. Remember the 7 basic functions. Remember those. So those will help you. Those are other different things that this graph could be. But for now, it looks like it's not a parabola. It looks like it's just a line because it falls at y equals mx plus b kind of form. So we'll say this is for 2. We'll say this is a line. And finally, it says use a grapher to support your answer. So we'll just graph them, both of these, and kind of see what we get. Okay, so I'll pull my graphing calculator. We'll go and hit y equals, and so at the top we will put, let's see, we'll clear that and we'll clear this. Let's see, the first one, x equals 1 plus t. So 1 plus, and again I can press the x button, and it now is t. So x equals 1 plus t. And for y is just t. Let's see. As far as a window goes, I think I want to graph the whole thing as much as I can. So I'll say the x minimum is negative 999, and the x maximum I want to graph 999 seconds, so I'll graph 999, and I'll graph that. And it looks like, if I zoom out a bit, this looks like a line. It looks pretty much exactly like a line. And that's because it is a line. This is exactly the same as a line. So when we did the equation and made it parametric, when we eliminated the parameter and got a line, that means we did the right thing. So we're good to go here. So we can say yes. We can say for step 3, or step 3, let's write at the top, we can say yes, we're good to go. Cool. The next question asks the following. It says use an algebraic method to eliminate the parameter and identify the graph of the parametric curve. Okay. And here it actually gives us those limits on t. It says negative infinity is less than t is less than infinity. It says we're going to graph the entire t. We're going to graph everything. So let's go ahead and eliminate the parameter again and kind of try to figure out what this curve looks like. This one might be a little bit tougher. Okay. To start off with, we will try to put it in function form as best we can. So we will solve for x. We get y equals t and x equals 8 minus 7t squared. So we'll solve for t for x. So we get, let's see, we get x minus 8 equals negative 7t squared. And we'll divide both sides by negative 7. So we get x minus 8 over negative 7 equals t squared. We square both sides. Remember when we square root, and this is really important for parametric equations, when we square root, we've got to have that plus and minus. Please don't forget that plus and minus. Very, very important for parametric equations. Okay, so we'll square root both sides. So plus or minus the square root of x minus 8 divided by negative 7. That equals t. Okay, now we know that that is t. We can go ahead and plug that in to our y equals. So y equals the plus or minus the square roots of x minus 8 divided by negative 7. Okay, so that looks a little bit weird. I'm trying to figure out what kind of curve is that a curve? Is that a line? Or is that a circle? What's going on here? Sometimes when you're left with something like this, the most helpful thing to do is realize, well, first of all, this is probably not a line, because a line looks nothing like this. One of the things you could do to try to just kind of get your head around what's going on here, there's two methods we can go, and I'll show both methods so you can kind of get the idea. One method is just to try to graph this. Another one is try to rewrite it so it makes a little bit more sense. So one is rewrite. So if we were to graph this, we have to remember we're not just graphing one equation right now. We've got this plus and minus. And that plus and minus means something really important, right? It means we now have two equations. Two equations that are similar, but not the same. They're actually opposites of each other. So y equals the positive version, x minus 8 over negative 7 is one equation, and y equals negative x minus 8 over negative 7. Now, why did I just do that? Why did I separate that into two equations? Well, because if you want to graph this, if you want to just plug it into your graphing calculator, you're gonna need to separate it and actually put two separate equations in. So if I was to go back to my function mode on the calculator, and let's go back to y equals. You'll notice that we have y1 equals this and y2 equals that. We have y3. We've got the y options, but we can only put in one equation per line. So there's no plus or minus button. So we've got to plug in the positive version and the negative version in order to make that work. And I'll do that in a second. But before we do that, let's look at what it means to rewrite the equation. If we rewrite this, let's try to rewrite it in a way that makes more sense. Square roots are really weird. I've never seen a form of a function that's in a square root. So let's try to get rid of that square root. Let's square both sides. So we get y squared equals x minus 8 over negative 7. And let's see, it'll look almost like we're undoing the hard work we did, but I think we kind of need to do that. I think we kind of need to do a little bit of that in order to make this make more sense. Let's see, if we multiply negative 7 on both sides, we get negative 7 y squared equals x minus 8. And I get rid of the negative 7 because I've never seen a form of a function. I've never seen a standard form like line, circle, parabola that actually had a denominator, that had a fraction. So we're going to get rid of that. One more thing we can do. Well, here's the last thing we can do. Let's just see what happens when we solve for x, because we're one step away from that. So we'll see, if we solve for x, we get x equals negative 7y squared plus 8. Now that's interesting. That looks like a parabola. That's the equation of a parabola. Y equals x squared plus b, or maybe more accurately, mx squared plus b. That's the equation of a parabola. Except instead of x, we have y, and instead of y, we have x. So I guess what that means then is that what we have is a inverted function. We've inverted it so that x equals y and y equals x, which means it's probably going to look not like a function, but like a function. Instead of a parabola, instead of going up and down, it's going left and right. Let's see how this looks. Let's see if that's true. And we actually graph it. So, but what the rewrite suggests is that it's a parabola. It's a inverted parabola. And let's see if that is confirmed by our graph. We're going to pull out that calculator again. And we'll plug in, let's see, for y1, we'll put in the square root. Second square root. And do x minus 8. And since I'm back in function mode, it uses x's instead of t's, which is good. And we'll divide that by negative 7. And for x2, we will, or sorry, y2, we'll put negative. Important, use the negative button, not the minus button, otherwise you'll get a problem. This negative button down here, not the minus. Because that does something very different, as you can see. So negative square root of x minus 8. I use the parentheses so that I don't, so that it divides the whole parentheses, not just part of it. Or divide that by negative 7. Okay. And we're going to hit enter. Or graph, it's probably more accurate. Oh, you can see it. So what I end up graphing here is a sideways parabola. And you can see now, this is really cool because what a parametric function was able to do for us is turn all of this into one giant line, to one giant curve. It was able to graph the top and the bottom at the same time. But if we use our algebra to convert it back into function notation, what the algebra tells us, what the function says, what it spits out is two functions. It says, no, we can't graph this as one function, but the algebra gives you two functions. It fixes the problem for you. It runs, because it can't graph it as a function, it automatically fixes it and says, okay, we'll do a square root and do a plus or a minus so that we can graph both halves of the function. And I think that's really cool. That's really cool how that works. Just to kind of give you a little more view of what's going on here, let's go back to parametric mode and graph the same thing so that you can see that it is the same function. At the top we have, let's say x1 is 8 minus 7t squared, and y is just t. Okay, and you can see we graph that. It graphs the exact same thing. So it's really cool, the fact that we can turn a parametric equation, a curve that's not a function. We can use algebra to figure out exactly what it would look like as a function, and the algebra fixes the problem for us by saying, this is not a function, but we will turn it into two separate functions so we can make it work. I just think that's so cool how that works out. How algebra fixes its own problems. So anyway, that's how you do that problem. We have confirmed that it is indeed an inverted parabola. And so that is our answer. Cool. The next question. Let's go up here. Okay, so match the parametric equation with its graph. Then identify the viewing window that seems to have been used. Okay, so normally you'd have a bunch of different options here for what the graph is, but really all I was asking you to do is just graph it and then kind of see where its limits generally are. So let's kind of do that. I want to pull out our graphing calculator again. and we're just literally just gonna graph it and see what it says. So 7 cosine, let's see, so cosine of t. Now we can't just do cosine cubed t. What this actually is, what cosine cubed t is, cosine of t cubed. And you might be more familiar with that. You might be familiar with that, or you might not be. But just remember that you can't put in cosine cubed t. You've got to put in cosine t cubed. So that's all that's happening there. And then for y, we have 8 times the sine of t cubed. Okay. And then we just hit the graph button, and there we go. Ooh, looks like we got a funky graph right here. So let's kind of see what the viewing window is here. So if we were to graph this, the extreme points kind of look like, we're going to find a more rigorous way to do this later. It kind of goes from -8 at the bottom as the y, and it goes all the way up to, what is that? Oh, I gotta turn off trace. It goes all the way up to what it looks like 8. So it goes from -8 to 8 on the y-axis, and it goes from, let's see, on the x-axis, it goes from it goes all the way up to 7 on the right side. On the left side, it goes all the way down to -7. Okay, so if we were to graph this, if we were to kind of just estimate a graph, we would draw a little bit of a parabola, or a graph, and we just do all these inverted parabola things. I think it's really cool. We can make this really neat diamond out of this. And we can say that if we were to graph, so it's full screen, it takes the full window, we'd say it looks like y, or -8, is less than or equal to y, which is less than or equal to 8. Or y min is -8, y max is 8. Now you can probably put that as well. You can say y min is -8, and y max is 8. And then for x, we'd say -7 is less than or equal to x, which is less than or equal to 7. Or you could write x min. X min is -7, and x max is 7. And that's it. That's really all there is to that problem. It's pretty straightforward, and I'm glad it is. The next one. It says use an algebraic method to eliminate the parameter and identify the graph of the parametric curve. Use a grapher to support your answer. Okay, let's break this down by clauses again. It says use an algebraic method to eliminate the parameter. That's step 1. And it says and identify the graph of the parametric curve. Okay, that's step 2. And it says use a grapher to support your answer. Okay, so this looks like a similar one that we've done before, except this one, unfortunately, is going to be a lot more difficult because we have this cosine and sine. What do you do with that? So normally, let's number these, 1, 2, and 3. Normally, if I was to write this down, so we get y equals 10 times the sine of t, and x equals 10 times the cosine of t. And just as a quick side note, I probably should have said this earlier, but if you're writing t in your own notebook, it's probably good to use the capital letter T, unless you want to write this really fancy curvy thing. If you write just a normal T, it looks a lot like a plus sign. So if you have like 10t or 10t and then b, I don't know, you could look like 10tb. It looks like 10 plus b, but what you mean is 10 times t times b. All I have to say, just make sure you're pretty clear with yourself so you don't kind of get yourself mixed up when you're writing down these letters. Okay, so you got 10 y equals 10 sine t, x equals 10 cosine t. That looks pretty familiar. It looks like a form that we've seen before. Or maybe So you may be able to already guess what this is going to look like, but we have to do this algebraically. We can't just like look at it and say, oh, that's what it is. We need to actually look at the algebra of this. And my first instinct, your first instinct might be to say, well, it's just sine. Let's just eliminate the parameter the way we've always done it. Let's try to solve for t, for x, and then then plug it into y. And how do we solve for t for x? Well, let's see, we'd go 10, we'd write 10 over 10, or is it x divided by 10? That would be like t equals the inverse cosine of I think that's x over 10. That's what you'd write. And you could say, well, we could just take the inverse cosine of that. Well, unfortunately, taking inverse cosines and inverse sines and all of that, that really is troublesome for us because it actually, remember how we said before that inverse cosine, we initially got the inverse cosine and inverse sine, or arc cosine, arc sine as people say it, that it actually has a very limited domain. Like inverse sine has a domain from 1 to -1, and inverse cosine has a similar limitation. Like look, so if we do this, we're going to be very limited with x. X won't be all that it's supposed to be. We're gonna have a problem because our domain will be limited. But we want to graph all the t's. We don't want to just graph just from negative 2 pi to 2 pi. We want to graph the whole thing. We want to graph everything. So it's probably best that we actually do some other method than what's normal. Here's a method that may work for you. Here's a method that does work. We have to pull out our trigonometry books or trigonometry chapters and try to work with this that way. If I want to try to get rid of that sine and cosine as best I can, and the one thing that you really want to make sure you always keep in your head, that one of the easiest ways to get rid of sine and cosine that we did all the time back in that trigonometry chapter was sine squared plus cosine squared equals 1. So if we can get something like that, then we're good to go. We can make this work. So let's see what we can do. So let's see, if we square both sides of the equation, then we'd be able to, of each equation, we get sine squared and cosine squared. Then if we can add the equations together somehow, if we can find some way to combine them, then we can maybe eliminate it somehow. Let's start by finding a way to get sine squared and cosine squared. So if I square both sides of each of these equations, I get y squared equals 10 sine t squared, all of that squared, and then x squared equals 10 cosine t squared. That reduces down to y squared equals 100 sine squared t, and we get x squared equals 100 cosine squared t. Okay, we're making progress here. We're making good progress, but we want to actually get rid of that sine and cosine. So how can we get those sines and cosines together so we can eliminate them and make them 1? Well, what we could do is we could just add the equations together. Remember from all the way from algebra 1, how we tried to eliminate things, eliminate different variables and solve by elimination. We would add two equations together. We can add this equation together and add that equation together, and it'll still work. So, really fancy stuff. I mean, if this is like the heart, this is like the genius of someone who's really got pre-calculus down. If you got pre-calculus down and you're making this kind of you're figuring these kind of connections on your own, and you're setting yourself up for a very good life beyond calculus. So, because pre-calculus is really just problem solving. But here's that idea. We're going to take y squared and x squared. We're going to add them together. So you get y squared plus x squared equals 100 sine squared t plus 100 cosine squared t. So we can almost combine them together. It looks like we can do this. We just need to factor out that 100, and then we can combine them together. So y squared plus x squared equals 100 times sine squared of t plus cosine squared of t. And boom, we've done it. We've kind of combined them together. We've got sine squared plus cosine squared, so now we can eliminate them. This just reduces down to just 1. 100 times 1. So now we have y squared plus x squared equals 100. And that, although it doesn't look like a function, well, it doesn't look very pretty at first. This is the elimination of the parameter. Now we no longer have t. We're using just y and x. If you wanted to go all the way, you could say, if you want to go even further, you could say, so y squared equals 100 minus x squared, and do y equals plus or minus the square root of 100 minus x squared. But I think you can work with this, and this would both be good answers. But if you do the first one, whichever one you use, you can kind of notice that it kind of has a trend from a previous kind of a problem we have. It fits a form. It fits the form of, let's get that make it look better. X squared plus y squared equals r squared. X squared, where is it? Yeah, y squared plus x squared equals 100. That is x squared plus y squared equals, well, what is 100? That equals 100. What squared is 100? That'd be 10. 10 squared. This is the equation of a circle. So we know, first off, we finished the first one. The second one is it's a circle. And you may have noticed all that already because this is the equation of a parabola. So this right here is the equation of a circle using parametrics. But this is the equation of a circle. We've now confirmed it, and we've kind of we've linked one to the other by eliminating the parameter. Finally, we need to use a graph to support our answer. Let's go ahead and pull out the graphing calculator, and let's close this. Let's start with the parametric form, and then we'll look at the other form. So 10, whoop, there it is. Finally, 10, okay, hello. I hope that's not this recording, because I'm still recording. 10 sine t, and then we have 10 cosine t. If you couldn't see that, I don't know if you could see the notification, but it said that it finished recording it finished putting a recording into my recordings. Okay, 10 sine t and 10 cosine t, that is a circle with a radius of 10. And that's exactly what it is. That's exactly what we have. So it's good. It looks exactly how we'd expect a circle with a radius of 10, because 10 is r right over here. Okay, now let's plug in the other equation. It's really cool. Again, the algebra is fixing the problem, because a circle is not a function. It is recreating the problem. It is recreating this problem in a way that is able to accommodate for the fact that it can't plot a function. It's making multiple functions so that it can be plotted. So when we have this y equals, we can't plot at y squared plus x squared equals 100 in the graphing part of our calculator, because it asks for y. It's what does y equal? So we've got to solve it for y. If we solve for y, we get plus square root 100 minus x squared. So we'll say square root of 100 minus x squared for the first one. And for the second one, we'll do negative, not minus, but negative square root of 100 minus x squared. There we go. And when we graph that, we get the exact same graph, except it's just now split into two different functions. So we can confirm we can support our answer with a graph. Good. And that's that problem. Let's move on to the next one. Find a set of parametric equations for the line that passes through -5, 6, and 3, 8. Well, we can do that. We have, just to do this, we'll just reference what we had in the very beginning, the notes we had in the beginning. A parametric equation. To start with, if you're given 2 points, we can use this right over here. Let's see if I can select it this time. There we go. I'm going to copy that, because that seems helpful. And I'm going to paste that right down over here. Okay, this little equation we have creates the line. Can I not paste? Well, that's a bummer. I worked so hard to figure out a copy, and I can't figure out a paste. There we go. Boom. To move over to text mode, but that's all right. Okay, y2 and y1. There we go. So this is our equation. All we've got to do is just plug and chug, and we'll have our answer. We'll have our parametric equation. We've already kind of gone over how this works, of how the equation works. So let's label this point 1. This is point 2. This is x and y. This is x and y. Okay. So x equals. Let's see. x1 is -5 plus t. This is why you want to use a little curly t instead of a t that looks like a plus, or maybe a capital T, that'd work too. Plus t times, let's see, x2 minus x1, so 3 minus negative 5. And let's see, we want to write y equals, let's see, y1 is 6 plus t times, let's see, 8 minus 6. And that's the equation. We just got to simplify and we're done. So we'll write, let's see, 3 minus negative 5 is 8. So we'll say, just to simplify a few steps at once, we'll get x equals 8t minus 5. And for y, we will get 2t plus 6. And that's our answer. Simple as that. That's all we have to do. And we're done. Cool? Cool. All right, next problem. Find a parametrization for the curve. The circle with a center -2, 3, and a radius of 4. Okay, so we've kind of looked at the equation of a circle before. And remember, let's go back to what that equation is. The parametric equation of a circle, that's right over here. That's x is r times the cosine of t, and y equals r times the sine of t. So I'm going to go ahead and copy that and paste it over. Important and helpful to have. So I'm going to go down here, and there it is. And I'll put text in. It's not really text, but you know, it's fine. And there we go. There's a little bit of extra down there. There we go. Cool. So we'll start with this. A circle has let's see. Let's plug in what we can, and then we'll see if we can move it around. The radius is 4, so r equals 4. So let's go ahead and plug it in first. So we get x equals 4 cosine t, and y equals 4 times the sine of t. So normally you think that would be done, but it doesn't have this. The center is not at -2, 3. So we're gonna have to find a way to move it to be -2, 3. Let's just graph what we have so far so we can kind of see what's going on. I'm gonna go to parametric mode, and up here we will clear everything that's in there so far. And let's see, we'll have 4 cosine t, and then 4 sine t. All right. So you can see we've got the graph. It's got a radius of 4, which is exactly what we want. But we want to move this graph. We want to move this circle so that it'll start at the point. That center will not be 0, 0, but it'll be -2, 3. This is where, remember how we did transformations? Think about it yourself. Can you find a way to do a transformation to make this happen? How can we transform x and transform y? Before I tell you, do you have an idea of how we can transform x and transform y to move the center? Well, we want to move x to the left by 2. So let's just experiment for a second and see what happens if I subtract 2 from x, from the x side. Well, that moves it 2 to the left. That's exactly what we want. Let's see if I try to move it. If I added 2, I'd probably do exactly what you'd expect. It should move it 2 to the right. That's because it takes whatever the t value is, whatever the answer should be for t, and it shifts it for as far as the x coordinate goes. It makes it go 2 to the left or 2 to the right, respectively, because we're just adding 2 to it. Great. So we can just subtract. If we want to move it to the center, has the x value of 2. The beginning has the x value of 2. We'll just subtract 2 from it. Subtract 2. And if we want to have it so that the center has a y value, starts with y value 3, we're going to move the entire circle up 3, then we can just add 3 to y. Oops, not just multiply 3, but add 3 to y. And that should get us exactly where we need to be. Great. So that gives us 4 cosine t minus 2. Let's actually choose a different color so we can make it clear. We've discovered something. I think it's worth a different color. So minus 2, and then plus 3. And that gives us our answer. That's close to the same color, but it's fine. It's cool. Great. And that's all we have to do. That's our answer. It has a center of -2, 3, and it's got a radius of 4. It satisfies all the things we need. And it's a circle. So we're good to go. With the next problem, it says the graph of the parametric equations x equals 1 minus the absolute value of t. Interesting, we've got these lines again, and you'll notice that I'm using the word absolute value instead of magnitude. Remember, magnitude is something that works with vectors. It's something that always works with vectors. We're no longer in the vector world anymore. We're now back into the absolute value world because we're dealing with numbers that don't have to do with, they don't have arrows next to them. We're just dealing with normal line segments and lines and stuff. So we can use these big double lines here. They just mean absolute value again, just like as we're used to, the way things are meant to be, perhaps. So the graph of the parametric equations, the first one is x equals 1 minus the absolute value of t, and y equals t minus 0.2. Y equals t minus 0.2. And let's see, it's from -2 to t to 2. So -2 less than or equal to t less than or equal to 2. Let's see. Oh, so that graph is given to the right. That's what the graph looks like. All of that is that parametric equation that looks like the thing to the right. Okay. So now we need to figure out what values in the parameter. We need to figure out what values between negative, what values the parameter. So that's the parameter is t. So what values of t that will produce the graph on the right in quadrant 1. So we want the graph on this right. We want this graph here, but we want it only in the first quadrant. We only want it just in this first quadrant here. Because remember what our quadrants are. I think you can probably rattle them off now. 1, 2, 3, and 4. We want it just in the first quadrant. Okay, so there's a bunch of stuff over here. There's a bunch of stuff to the left of it. This over here and over here that the graph makes, and we don't want any of that. We just want the t that will give us that stuff right in the center. This stuff over here. So we're gonna figure out how to calculate. Oh, it's like Christmas. But we're gonna figure out how to calculate just that. How to limit t so it's just that. Well, what do we know about the first quadrant? What are things that we are aware of, that we're sure of about the first quadrant? Things that are always true about the first quadrant. Well, we only have positive numbers, right? And positive numbers means that as far as x is concerned, or as far as the graph is concerned, this is all x is greater than 0. X is greater than or even equal to 0. Well, actually, no, the full first. That's the boundary line is equal to the full thing. If you just want just the quadrant, it's x is greater than 0. And if you want just the first quadrant for up and down, we know it's not going to go negative, so it's always going to be positive. So we'll say that y is greater than 0. Let's see if we can apply that. If we can limit it so that x will always be greater than 0, if we can ensure that x will always be greater than 0 and y will always be greater than 0, then we can confirm that we can find a way to limit this parameter. We'll have something that will be limited from -2 to 2. So let's see if we can do that. Okay, x is greater than 0. Let's see, how can we apply x is greater than 0 to this? Well, here's something we can do. Well, we know that x is 1 minus the absolute value of t, right? And we want x to be greater than 0. So what do you think will happen then? Here's a guess. What could happen if we want x to be greater than 0, then what we want to write is, if x is 1 minus the absolute value of t, we can write 1 minus the absolute value of t is greater than 0. Yeah? Let's do it. And let's see what this gives us. So in this way, we can actually solve for t, see what variables we have for t. So let's see, we'll add the absolute value of t on both sides, because we can actually add an absolute value. We get 1 is greater than the absolute value of t. Okay. Okay, now we need to get rid of that absolute value. Remember how we split up an equation with absolute value to do that? Well, what we're going to do is, what we'll need to do is we will take, let's see, we will take this, we'll take it and we'll multiply, we'll split it up into two equations. So one's going to be 1 is greater than the negative of t, and 1 is going to be greater than the positive of t. Two versions, one where it's negative and one where it's positive. We're going to solve for that. Okay, and we will see let's see, if we solve for the left one, the right one's already solved, which is this is t is less than 1. That's the right side. The left side, we need to actually do a little bit of division here. We'll divide both sides by -1. Divide by -1. Divide by -1. But remember, if we divide by a negative, what do we have to do? We've got to flip this sign. So that's what we'll do. We'll flip the sign. So we get -1 is less than t. There we go. Now we've solved for t on both sides. Okay, so I guess with that, if we limit it all that way, we get -1. -1 is less than t, which is less than 1. Cool. That's interesting. So we just plugged in a parameter. We plugged in a limitation for x, and out popped what it kind of gave us is so hey, if we plug in this parameter, then if you say that x will always be greater than 0, then what I'm going to tell you, what this equation tells us, it just literally just tells us. It says, well, then you've got to know that -1 is less than t, and t is less than 1. T is going to have to be between -1 and 1 at all times. So right now we've got a first limitation. We've got a -1. Less than t, it's less than 1. That's the first bit of our parameter. That will guarantee that x will be greater than 0. Great, that's perfect. Let's see if we do the same thing with y. I bet it'll fix the other side too. It'll tell us any other parameter things we need to know in order to get this down. Okay, let's plug in y is greater than 0. We get y, let's see, so if y is greater than 0 and y is t minus 0.2, then what that means is that 0t minus 0.2, which is y, has to be greater than 0. Excellent. Okay, solve for t. This one's a lot easier to solve for t for. And we'll say t equals 0, or sorry, t is greater than 0.2. I'm adding 0.2 on both sides. Remember, if we add or subtract a negative, then it doesn't change the sign. It's only when you multiply or divide. So t is greater than 0.2. Okay, so if what we found out is that if -1 is less, or let's put it this way, if x is greater than 0, then we've got -1 is less than t is less than 1. If we've got y is greater than 0, then we know that t has to be greater than, or maybe we can put this another way, trying to keep it all synced up. 0.2 is less than t. It has to be some number that's greater than 0.2. T is always going to be some number that's greater than 0.2. So if we want it to be x is greater than 0 and y is greater than 0, then that means that we need to find some way to combine these two together. Now let's think about what it's saying here. It's saying -1 is less than t is less than 1. So we'll draw a number line. This is -1, and this is 1. And so t has to be somewhere in the middle. This has to be t for x to be greater than 0. Okay. Or maybe we can write between these two variables, x is greater than 0. Okay. Now if I wanted to do 0.2 is less than t, or t is greater than 0.2, then we would write something like this. Let's change the colors. We would say, let's see, 0.2 is greater than -1. It's actually about right over here. 0.2, and y would have, and if t is greater than that, it'd be everything here and beyond. Okay, so that means in all the y area, this is where y is greater than 0 for t. Okay, so if we went quadrant one, which means we want both to be true. We want it to be true that x is greater than 0 and y is greater than 0, which means what we want we want the places where x is both greater than 0 and y is greater than 0 at the same time, which means we want the place where they intersect, this section in the middle between 0.2 and 1. So another way to think about it is if we put an and between -1 is less than t is less than 1 and 0.2 is less than t. If you're familiar with ands and ors, it would reduce down to that exactly. We'd have 0.2. Let's put this in the yellow color or red color so that we're clear here. 0.2 is less than t which is less than 1. And that gives us the exact parameters we need in order to do this. We can confirm it with the graph. Let's actually see the graph and see how this works. Okay, so if I take if we take these parameters, we have 1 minus, actually clear, 1 minus the absolute value. Ooh, absolute value. I've almost forgotten where the absolute value is. I should know that. Let's see, absolute value is, no, math, that's in math, isn't it? No, it's not in math. Oh gosh, I'm sorry, I'm wasting your time. Math numbers, absolute value, there you go. So, I went to math number abs, or which is number 1. And let's see, absolute value of t. And then for the y1, we will have t minus 0.2. And let's see, we'll graph that. Actually, change the window. And that's it. If we graph the whole thing, we get the whole graph. And this is everywhere. But it says initially the graph was limited to negative 2 to 2. So we'll limit our t from negative 2 to 2. And that gives us the graph, it gives us the graph that we're used to. Right over there, right on the right, right there. Okay, now let's see what happens if we do the first one. If we do the first limitation, negative 1 and 1. If we do negative 1 and 1, we get just, x is greater than 0. Only the places where x is greater than 0, that's negative 1 to 1. You can see it's only the right side, x is greater than 0. Now if we changed that a little bit, we said, let's go back to let's say negative 999, because it doesn't, we would say start with 0.2. I'm going to clear that, 0.2, and go all the way up to, it doesn't matter how high, then we get all the values above the y-axis. The y is greater than 2. If we want to limit it back to the constraints that it had before, the initial constraints, we could put 2, because it is initially between negative 2 and 2. And we can see it's just values that are above 0. It's above values that are above the x-axis. And so if we want to do both of them, we want to do the values that are between 0.2 and 1. Because that's the things that satisfy both of them at the same time, between 0.2 and 1. And that gives us that section right down in the middle, right there. Cool. So that confirms it. This is that little section we're looking for, that section in the middle, and just in quadrant 1, and that's how we find it. Great. All right, let's look at this word problem. Ron is on a Ferris wheel of radius 25 feet that turns counterclockwise at a rate of 1 revolution every 15 seconds. The lowest point on the Ferris wheel, at 6 o'clock, is 20 feet above ground level at the point 020 on a rectangular coordinate system. Find parametric equations of Ron as a function of time t in seconds if the Ferris wheel starts t equals 0 with Ron at the point 2545. Okay, so even if you're the brightest of people, it's easy to get lost in everything that's being said there. In fact, you probably are lost at everything that's getting said there. I'm lost with everything that's getting said, everything that's said there. Let's see if we can break down what it's actually saying, and then what it wants from us, piece by piece. So Ron, okay, we got a guy named Ron. He's on a Ferris wheel, a radius 25 feet. So let's go ahead and draw a Ferris wheel then. So that's our Ferris wheel. And it says it's got a radius of 25 feet. Ferris wheel has proper carriages. Let's put proper carriages because that's the way Ferris wheels work. Okay. Actually, that'll do. Okay, and then we'll say the radius is 25 feet. Okay, good. We got the first part down. And we're saying it turns counterclockwise. Let's see, that's the first part. And it turns counterclockwise at a rate of 1 revolution every 15 seconds. Let's start with the first part. It says it turns counterclockwise. That's one thing. So let's see, it turns counterclockwise. It goes that direction. And it does that at a rate of 1 revolution every 15 seconds. So 1 revolution every 15 seconds. Okay, so let's see, that'd be, it's hard to kind of write that. We can just say, 1 revolution every 15 seconds. Because there's not really an easy way to image that, to draw an image of that 15 seconds, of 15 seconds passing. In fact, that's what polar coordinates, or sorry, parametric equations are for. They're for graphing time when we can't just graph time on a piece of paper. The lowest point of the Ferris wheel, 6 o'clock, is 20 feet above ground level. Okay, so let's see. The lowest point is 20 feet above ground level. 6 o'clock, if you think of a clock, let's see, we got 12 at the top, we got 6 at the bottom, 3 and 9. So it's saying right at the bottom of the Ferris wheel, we've got 20 feet above ground level. Okay, so what that means, let's see, that would mean then that this distance from here to here, from the ground, let's say this is the ground, let's make a little green ground here, ground level there, let's say that's 20 feet. Okay, and maybe we should just make some supports here just so it kind of looks decent. Okay, that's our Ferris wheel. And it's 20 feet above ground. And we're going to call this point that it's at, it's at the point 0, 20. Okay, so that means that this point right here, this point right at the bottom of the Ferris wheel, is the point 0, 20. Well, that's something that's helpful. If it's 0, 20, that means we can draw coordinates for everything else as soon as we can. Before we even move on, let's just look at that. Let's look at that just one section and see what that means. What can we gather from that? Well, if we draw some coordinate system, let's draw some coordinates. Let's see, if that's 0, 20, that must mean that the y-axis goes straight through it because it's 0. It's 0 for x, which means that's the y-axis. And if it's 20, if the Ferris wheel is 20 feet above ground level, that means that ground level, quite understandably, naturally, is 0 on our axis. Okay, so we got, let's see, this is that center point, that bottom is 0, 0. So you go from 0, 0 to 0, 20. Let's see if we can quickly graph some other points that we can see on this, other points that have been discussed so far. So we got, if this is a radius of 25 feet, that means the center of the Ferris wheel would have to be 25 feet above the bottom. So this got to be this is a radius of 25 feet, as before, 25 feet, because that's the radius of the Ferris wheel. So that means that center would be 0, 45. Okay, cool. Let's see, if we went all the way to the top, we could say that's 0, I don't know, 70. Let's see, if we went to the left and right, we'd say it is, on the right, we'd have, let's see, that's 25 feet to the right, so we had 25 to the x side, that'd be 25, 45. And then left, we'd have the opposite, negative 25, 45. Great. I'm just labeling some points here so I can get a better bearing of what's going on and how we're moving. Usually that's kind of a helpful thing to do. What can I know? What can I learn? What can I figure out about this before I even move on to other things? Okay, so I think it's about all I can really gather. That's all the points I can really kind of identify from this, from that value of the point 0, 20. So let's move on to the next section. It says 0, 20 on a rectangular coordinate system. Oh, never mind. This is all part of one clause. Part of one clause, 0, 20 on a rectangular coordinate system. The rectangular coordinate system, if you're curious, is just the coordinate system we've always been using, where there's x, you choose x, y, you choose an x value and a y value, and you plot that point. There's something called the polar coordinate system and other things like that, but rectangular is just what you're used to. So you can even forget that phrase, rectangular coordinate system, because that's all we know right now, or for the most part, that's what we know. Okay, find parametric equations. Okay, great. So now it's giving us something to do. It says find parametric equations. So our goal, this is our goal. This is step 1. We want to find parametric equations of ρ as a function of time, t. Of ρ as a function of time, t. Well, what's ρ doing? Oh, Ron's on the Ferris wheel. Ron's on the Ferris wheel. So we're going to make an equation of Ron going around the Ferris wheel as a function of time. If the Ferris wheel starts with t0, let's see. Oh, one more piece of data. If the Ferris wheel starts at t0 with Ron at, or t equals 0, Ron with the point 25, 45. Okay. So we're at 25. So we're going to start at point 25, 45. Oh, that's the right point. It's the point on the far right. It's a good thing we mentioned that before. So this is the starting point. This is the starting point, and that is also t equals 0. So t equals 0 is this right point in the middle. We want to start there, and we're going counterclockwise, and we're doing all that. And we just need to graph. We need to make an equation that represents this movement. Okay, one of the first things you might notice here is that we're trying to graph this movement around the circle. And this movement around a circle, well, that's just circular motion. That's a circle motion. So all we need to do then is, well, first thing we need to do is find the equation of a circle, which you may remember from the beginning of this lesson. This is the equation of a circle. X equals r cosine t, and y equals r times the sine of t. There we go. Oh, that's not going to copy perfectly, but we'll make do with it. And and one more thing, 2 pi equals 1 revolution. So we want to keep that in mind as well. So let's see, let's paste this on over. And paste. Great. Okay, so r sine t. Okay, and it's also important helpful to know that 1 revolution, I think there's also noticed on the side, there's 2 pi equals 1 revolution. Okay, so if we're trying to do 1 revolution every 15 seconds, let's first figure that out. We're trying to do 1 revolution every 15 seconds, and 2 pi is 1 revolution. So we're trying to do 2 pi every 15 seconds. So that's what that means. We're trying to do 2 pi every 15 seconds. Okay, so that seems about all I can figure out there. There's maybe a little more we can go there. We're going to come back to that in a second, though. We got this equation of a circle. I'm kind of jumping back and forth. Let's focus on the circle first, because let's get that done. So a circle, this is the equation of a circle, and if that's the equation of a circle, then what we can do is just plug in the values we know and see if we can recreate that circle. So let's see. It starts asking for a radius r, and when you can find that, the radius r, that's just 25 feet. We're given that. So let's go ahead and plug in 15 feet. So x equals 15 cosine t, and y equals 15 sine, not 15, excuse me, 25. These are 25s. 25 sine t. Hope I didn't confuse you there. Now, you might look like we're done here, but we should probably graph this and see what that looks like. This is, let's see, 25 cosine t and 15 sine t. Ooh, let's actually pull up the Desmos here. So 25 cosine t and 15 sine t. That would be, I'm gonna put the official jargon for Desmos. So we're gonna put in 25 cosine t, and this is nothing that's super official. It's just what Desmos needs in order to understand what's going on. I'll put a comma, so x coordinate first, and then 25 sine t. So 25 sine and t. Let's see, cube. I just put in t. There it is. All right, cool. And okay, it's asking for boundaries of t. Let's say t goes from 1, and let's say its endpoint is the same thing as before. Let's say it's b, and we'll add a slider for b, so we can kind of move b around. Okay, great. Maybe say b starts at 0 and goes to 2 pi. No, let's just say 10. 10's fine. Okay. So if I want to zoom out to see what's going on here, okay, if I zoom out and I start graphing this, hey, here's something that's interesting. We start on the right side, like a normal circle. He starts in the, if we were to graph this, we start on that far right side of the circle and we start going in a counterclockwise direction. Okay, so the equation that we have now, if it were regraphed, it would do exactly what we'd expect with Ron, in the sense that exactly what we want. It starts in that right side, that far right point of the circle, and it goes all the way around in a counterclockwise direction. So if we go back to our work here, our different qualifiers, let's see, we can say it turns counterclockwise. It turns counterclockwise, and it's got a radius of 25 feet. We did that too. Let's see, what else did we find? Yeah, the initial point is on that far right side. It's not the point 2545 yet. We'll get to that in a second. Let's first focus on that rate of 1 revolution every 15 seconds. Let's get back to that and solve that. We want 2 pi every 15 seconds. Let's get that third point. So 2 pi every 15 seconds. Well, that means, let's see, if we want 2 pi, that means every time I put in t, so if I put in 1, if t equals 1 or 2 or 3 or 4, I want the theta, I want the angle we put in to be not just 1, but I want it to be 1/15th of 2 pi. I want it to be 2/15ths of 2 pi. 1/15th of 2 pi. I want this to be 2/15ths of 2 pi. And so on. So I want to keep adding 15ths to 2 pi so that when I get to 15 seconds, I'll get 2 pi. Okay. So if I want my angle to do that, then I would say instead of just t being 1, 2, 3, and 4, if I want it to go that slowly, then I want this to be, I want t to work in seconds. Then what I want to do is I want to say, instead of putting just t here on the right, let's change this so it's not just t, but we'll say if I do t times t over 15, 2/15 times 2 pi, that will get me the exact kind of movement I want, so that after 15 seconds I'll get 2 pi. So let's go ahead and replace that. So that's t over 15 times 2 pi on the right. I guess to use gray. I meant to use green. Oh well, this will be fine. And then t times 2 pi over 15. So in theory, that should make it so that after I pass 15 seconds, I should get a full revolution. That third qualifier at a rate of 1 revolution every 15 seconds. Let's go ahead and put that in Desmos and see if that does that. Okay. Let's see. So that'd be okay. Let's go ahead and make sure that I got my cursor in the right position. There we go. Well, that'll be good enough. That'll be fine. That'd be, let's see, that's t times 2 pi. T times, let's see. Oh my, I'm not versed in this well enough. Times 2 pi divided by 15. Okay. And that's the same thing as saying t over 15 times 2 pi. It's just I just moved it around a little bit. And we'll do the same thing on the right side. So we'll get t, or just change, I just moved the 2 pi around a little bit and the 15 around a little bit, but it does the same computation. It's the same math. T times 15 divided by 2 pi. Great. All right, that looks a little bit weird. I did it backwards. Excuse me. T times 2 pi over 15. Excuse me, I'm sorry I got this wrong. Here we go. T times, good thing I caught it though. We could have had a disaster. Okay. D times 2 pi, that looks a little more normal. Okay, let's make sure our B slider goes all the way up to 15. So that if I finish the B slider, it should, in theory, go all the way around once. So if I go, it chugs, oops. If I goes and it starts chugging along, if I get to 15, it does 1 complete rotation. Perfect. So by the time I get to B equals 15, I do 1 complete rotation. 15 seconds. If t gets all the way up to 15, then I have a 1 complete rotation. So this works perfectly. This is exactly what we want. Okay, so that's good there. So we've got that bit down. One revolution every 15 seconds. We've got that down. It says the lowest point on the Ferris wheel is 20 feet above ground level at the point 0, 20 on the rectangular coordinate system. Okay, so that's the next thing we've got to cover. The lowest point is 20 feet above ground level. And, oh, yeah, that was just where we found all the points is located at. It looks like the center of this circle is at 0, 45. So we're going to find a way to translate this entire graph up 45 units. Let's see what we can do to do that. Maybe you can think about this yourself. Maybe you have the idea of how we can translate this circle up 45 units. Well, here's something we can do. We can go to the y position. Oh my, let's undo that. Didn't mean to delete it. We go to the y position, and we can add 45 to it. And that'll bring it up 45 units. And you can see the bottom of it hits 20. Here's what I just did. I went to the equation, and I said, let's go ahead and add 45 to y. And you'll see, normally we started in Desmos, you would notice, let's see what Desmos shows you. Desmos would show you something like this. Something like that. That was a circle as it was in Desmos. But by adding 45 to it, it shifts it up. So the center is no longer at 0, 0, but its center is now at that 0, 45 section right there. Okay, so perfect. That does exactly what we want it to do. Okay, good, good. Let's see. So that means that is good. There we go. And, oh, yes. Lowest point is actually, that's not the right one. The lowest point is 20 feet above ground level at the point 0, 20 in the rectangular coordinate system. So that hits it. So if we go back to this circle, yeah, it hits 0, 20. That's exactly where the bottom is. Okay. So we just finished that. And so we found this equation. Let's see, the last condition is the Ferris wheel starts with t equals 0 at run at the point 25, 45. Let's make sure that that's what that's doing. Let's see, at the t equals 0, where do we start? Right when we start out right at that point on the right, in the far right. And what is that point on the far right, right at the bottom? That is the point, well, actually that's the point 25, 45. That's exactly what it is. Because we lined up the circle exactly as we needed to, and we lined it up perfectly, it just naturally put that right side in the position 25, 45. So it looks like we're good here. This condition here is accomplished. We've solved it. So that means that we have done exactly everything we need to do. We found a parametric equation of run as a function of time, meeting all those conditions and all those things that we've talked about. So that would mean that this right here, what we've just found, is our answer. Okay, a lot to do there, a lot happening. But if we just, again, if we chunk it down piece by piece, it becomes much, much less of a monster, as long as you take one small piece at a time, taking bite-sized chunks. Okay, and then I think one of the things that really helped us the most in this one was the fact that is that as soon as we found something, we went with it and ran with it, and we saw, what can we learn from this? What can we discover from this? Like, for example, when we hit that point 20 feet above ground level and 0, 20 on the rectangular coordinate system, when we found that, we just found a bunch of different points. We found the point 25, 45, and 0, 45, and 0, 70. I think doing that really helped speed things up a bit so we could figure things out. So while it seems like we're going off on a tangent, just exploring those things kind of really helped us in the long run. So when you do get a math problem and it's a bunch of words, just figure out what it means and then explore and learn and say, okay, what does it mean when it says these things? What can I learn from this new bit of information, especially if I combine it with previous old pieces of information? If I put all of these different pieces of information together, what are the new things that I can discover with just what we have, just this new information that I'm adding to my base of knowledge? Anyway, cool. All right, next problem. A particle moves along a horizontal line so that its position at any time t is given by s of t. Write a description of the motion. Okay. S of t equals 1.5 t cubed minus 4t squared plus 4t. Negative 4 is less than equal to t, which is less than equal to 7. Okay. So this looks like it looks like it's trying to be a parametric equation, but it's not a parametric equation. You know what I mean? It's not. It's like it's just a. This is just a normal equation. This is not. There's no y and x equation. It's just a normal function. So we could go about this in a couple different ways if you wanted to. We could say y equals 1.5 t cubed minus 4t squared plus 4t, and then negative 4 is less than or equal to t is less than or equal to 7, and we can say x equals, well, just t. And so we could do something like that and then graph it, or we could just eliminate the parameter right here and we could just say that y, or we could just say y equals 1.5 x cubed minus 4x squared plus 4x, where negative 4 is less than or equal to x is less than or equal to 7. And we just got to remember that when we say x, we actually mean t. We actually mean the time that's movement. And so we could actually just graph this like a normal equation, and this would work out fine. If we pull out our calculator again, and if we do both of those, we'll see that it actually gets to the same thing. If that already makes sense to you, so why these are the exact same thing, you can skip this next bit. I'm gonna go ahead and graph both of these just to show, hey, these two statements are saying the same thing. So we have y1. Let's say if we were to do the parametric mode, let's start with parametric because that's the first one that's listed, and we will say x1 just equals t, and y1 equals 1.5 times t cubed, and minus 4t squared plus 4t, and end parentheses. And that'll give us a graph that looks something like, I should zoom in so it's a proper viewpoint. Oh wait, I forgot. I want to make sure I don't forget. The minimum for t should be -4. That's our boundaries. -4 is the minimum. I just hit window to make for minimums and maximums. So we'll say the minimum is -4 and the maximum is 7. Okay, we'll graph that, and that gives us this neat looking graph here. Okay, so as I go right on the axis, as I go further and further right, I'm going further and further in time, because the x-axis, x is t. The x-axis is the t-axis. So as I go further right, I go further in time, but we've limited t, so it goes so that t is only calculated from -4 to 7. Okay, great. Okay, well, so that's the parametric equation. If I did the function equation, if I did the function version, which should be the exact same. We'll check to make sure that it is. That is not exactly what I wanted yet. We'll have 1.5 times x cubed minus 4x squared plus 4x. And okay, for our window, I can't do a t thing here, so I just gotta limit the boundaries of the window itself. I gotta say the boundaries of the window are gonna be my limits of x. So x goes from -4 to 7. Okay, and y min and y max gonna be crazy. So let me just go ahead and reset those to the standards, because it looks like I was just doing something strange before. Okay, and it looks like we got the same graph here. Yeah, we do. We have the same exact graph here, and we're doing the same thing. It looks exactly the same. It's just that I can't just limit it. I can't just limit the actual drawing. If I were to zoom out for x and make x greater than, because you can see it stops, but the limit of my x side is -4. I can't. The limit of the actual calculator is -4, and the limit of the actual calculator on the right side is 7. So I'm actually making firm limits here. I could zoom out. If I were to zoom out, I could change those limits and kind of see that it keeps going further. The advantage of using the parametric version is that I can make it so it only graphs from -4 to 7. It only graphs -4 to 7, but I could zoom out and see whatever I want to see. Okay, but the point is, they're the same graph. So let's go back to parametric mode so we can kind of see that same graph again. Let's see again. Yeah, here it only graphed from -4 to 7. I could zoom out as much as I want to and try to look at more, but I've made clear limits on what t can be. Whereas you can't really do that with the function version. Okay, because there's no t. Okay, great. So we've got this, and it's all this said. We've kind of just made a big wind up, and I kind of went on a huge tangent here, just exploring the graph. So that's kind of fun. But it's saying write a description of the motion, and it gives us a bunch of blanks it wants us to fill out. Okay, the particle starts from s-1 equals, let's see, s of -1, so t-1 So s of -1, that means t equals -1. That's what it's saying. Okay. So let's say that's -1. Let's look at that. So at -1, at t equals -1, it starts right about. I want to trace that right onto -1. Let's see. So we say t is -1 there. You see that t is -1. Yep. And y equals -13.506. Okay. So we'll say so that when t equals -1, so s of -1 is s of -1. Just to make it very clear what I'm doing, -1 is our t because we're doing s of t. We're saying when -1 is t, what is s of t? What is our y? And the same as like what is f of x? What is our y? Our y is -13.506. Okay. And then what's it doing? It's moving up. Yeah, it moves. After that, after we go to the as we go to the right, as t increases, as we go further up in t, it kind of moves up. All right. So it moves up for how many seconds? Let's see. Well, we can see when we graph this, it doesn't move up for forever. It actually stops at a certain point. It stops right between what looks like 0 and 1. It's sometimes somewhere between 0 and 1. It kind of changes direction. Now, if you have a standard TI-84, you can just press second and then trace, which if you calc, and you can calculate a maximum, and it'll let you choose left bounds and right bounds and a guess, and then it'll just give you what the maximum is. But unfortunately, I'm not using a calculator that's like that. So I'm going to give you another way to do this through your TI-84 if you have your TI-84, or if you're using a graphing calculator like mine, that's just an app. This would also work. So we'll go to, in order to find the way to do this, we'll go to math, and let's see, I believe, yeah, it is f. We're gonna find the maximum, so we'll do f max, and we'll put in the actual variable. We'll have to put in the actual function, and so we're gonna put in the full thing. So it's 1.5 times t to the third. You notice that because we're in parametric mode, it still is t. When you press the x, t, theta, n, it still stays as t. Minus 4t squared plus 4t. This is a place where the parametric mode actually works in the main calculator. Oop. Yeah, so that's what I put in parentheses. Okay. And then we'll need a comma. Now I believe a comma is right above the 7. So that comma button. And our variable is t, so we'll put in t. And let's see, the low value that we used for t, we said we want to find a maximum between 0 and 1. So we'll put 0 for our minimum, or for the low point, for the start point. And then for the end point, we will put 1. And then that last thing is an optional. We don't have to put anything in there for that. That thing in braces. And we press enter, and it'll give us an answer. Great, 0.66. So that is 2/3. So let's see. So it moves. It ends at t equals 2/3. So we'll say it ends. It changes direction at t equal as at 2/3. S of 2/3. What is s of 2/3? What is that point? If we were to actually just go back to the graph. Oops. I don't know how that happened. I'm not entirely sure how that happened. Let's keep that there. There we go. Sometimes I feel like I'm a decent person with technology, but then I go in front of a camera and often and just immediately I'm terrible. I don't know what that is. Okay, and you can see right about at t equals 2/3, we can hit that maximum. So as long as I'm on trace here, I'm gonna keep tracing. T equals 2/3, and so the y value becomes about 1.77. Yeah, about 1.77 is what that is. You could also just calculate this. Here's a way to calculate it if you like. So 1.77. If you want to go back to the normal calculator, here's a way to actually do that calculation. We could plug in 1.5, we can plug in the actual calculation, 1.5 t cubed. Actually, we'll say this. We'll say 2/3, 2 divided by 3. We're going to store that as t. Okay? And then we're going to run the calculation. 1.5 times t cubed minus 4t squared plus 4t. Okay. I think this is 1.77. Exactly. Well, okay, so maybe 1.78 is more accurate if you round. There we go. So that's 1.88 or 78. Great. And now that I have that in there, I can plug in any other number I'd like to. I can plug in, say if I want to figure out when t equals 5, I can say 5 store t, and then just tap on the old value and run the number again, and it'll give me what the new value is. But that's something else. That's the only way I'd like to do that. But that's another way to graph it, and that's a way to make it more and more certainly accurate. Okay. So we just found the maximum. If you ever forget about how to do the maximum, how to find the maximum or minimum, I've got a little note on the right side of this equation, of this I guess notebook, right over here, that kind of summarizes how to do maximums and minimums with just through that function mode that I just did. We'll do it again. Let's see. It says it moves up for how many seconds? We don't know how many seconds. Let's see. We started at a -1, and we went to 2/3. So we start. If we were to graph this a little bit, we start at -1. So let's see. We go -1, then we go to 2/3. So it moves up for how many seconds? It moves up for 1 2/3. So 1 2/3. 2/3. Okay. Or you could say, if you want to write it as a normal improper fraction, you could say 5/3 seconds. Changes directions at 2/3, which s of 2/3, which is 1.78. And then what does it do next? Well, we know from the graph that it moves down for a little bit. After it finishes that, it goes in the downward direction. So we went up. Now we're going down. And it's going to go down until it hits this valley down here. And we got to figure out what happens, what that value of that valley is. What is that? And so let's see. We'll pull it out. Well, actually, before we do, let's make sure we write down. And let's see. Where's it going to hit? We don't know how many seconds it'll be, but first we're going to figure out where it actually ends up before we figure out any of that. So let's go ahead and run our fmin before we figure it. Yeah, fmin. So we will plug in the same equation. Fortunately, I can just tap that equation again because I plugged it in. That's our function, and then our variable is t, and then our low. Ooh, what is our low? Let's go look at the graph again. So we started at, let's say we want to figure out when that trough is and that bottom part is. It goes from maybe, like I said, from 1.5 to 2.5. That seems to be a good place to find that trough. So 1.5 is the first part, is the left bound. The right bound is 2.5. And good. And parentheses, enter. Okay, 1.9999. Let's just round it up and say it's pretty much 2. It's essentially 2. There might be just a tiny bit of graph error there, but that seems to be 2. So it goes from, it changes direction at s of 2. And so that's 2. And so how long is it going down for? So if it starts at 2/3 and then goes to 2, that means it's been moving for 1 1/3 seconds. So it's 1 1/3 seconds. That's how long it goes down for. Changes direction, s equals 2, s of 2. What is s of 2? Well, we'll just plug that in. So we'll say 2 is t. 2 stores t. We'll hit that function again, 1.5 of all that, and that's 0. That is a 0 of the function. So s of 2 equals 0. And then what does it do? So after it goes down, it goes up afterwards again. So it goes up for how many seconds? How many seconds does it go up for? It goes up for until we hit the end. So let's see. let's see, it goes from 2/3 to 1 and 2/3. Well, it goes from 2 to all the way to the ends. And let's see, S of 9 is where it ends. S of 9 is where they say the endpoint is. I think actually this is a, I compiled two questions together. This should be a 7. I think in your problem it's going to be a 9. But S of 7 is probably the endpoint. So from 2 to 5, it goes, sorry, no, 2 to 7 is the endpoint. So it ends. We start at -1, it's high of 2/3, low at 2, and it ends at 7. So we go from 2 to 7. That means it goes up for let's see, 5 seconds. And it ends up at S of 7. So 7 store T. And we'll plug in that equation again. And that gives us 262.5. Yeah, all right. Well, I guess that's got to be our answer, 262.5. 262.5. And that's it. That would be all of our answers. Put those in the boxes and you should be good to go. So that's the same. That's how to solve that kind of problem. We're just kind of looking at the graph and describing how is it moving and what is it doing, what kind of changes is it making. So that's all we're doing there. Okay, for numbers in 10, 11, you're gonna be on your own. I think they're pretty similar to the other problems, but I think you can do them. So we'll just do the best you can there. Let's look at the last problem that's available for us today. That's the last problem, isn't it? Yeah, that's the last problem. Okay, graph the parametric equations x equals 9 minus t squared and y equals 5t in the specified parameter interval. Use the standard viewing window. Okay, standard viewing window, first of all, let's get that out of the way. Standard viewing window is x, well, yeah, x min is -10, x max is 10, y min is -10, and y max is 10. If you are on a TID4 and you press the zoom button and then after that you press standard, zoom standard, you will get this right here, -10, 10, -10, 10. And the reason why this is your calculator is like a box, and it's trying to kind of trick it. It's actually a rectangle. It'll be a little bit spread out a little bit, but that is the standard way of viewing these things. So let's go ahead and do that. Let's make a before we do anything, let's make sure that we get our parameters correct. Well, actually, let's just graph it. Let's do the graph first, and then make sure our parameters are correct, because that's what we normally do. So we're gonna put in x1 is 9 minus t squared, and y1 is 5t. Great. And then our viewing window, it says the standard viewing window. So x min needs to be -10, and x max is 10. And you can just, as soon as you start typing, it clears everything out. So that's pretty nice. Y min is -10, and y max is 10. If you were curious, the t steps says how many times or how far are we going to go before we plot another t. In other words, it'll evaluate at t equals -4. If its t step is 0.1, that means it'll start at evaluate at -4, make a plot at when t equals -4. Then it'll evaluate at -3.9 and do a plot at 3.9, and then 3.8 and do a plot whatever their answer is for 3.8. If you did t step is just 1, then it would evaluate t equals -4, and then plot a point at -4, and then -3 and plot a point at -3, -2 and plot a point at -2. So you want a small number here, 0.1, and usually the standard is fine, but I just want to kind of explain that if you're curious. The finer it is, the smaller the number, the more clear-cut and accurate your answers will be, and the more accurate your graph will be. However, the longer it'll take to graph. So just keep that in mind, because the processor calculator has to graph every little last dot and do every single computation. But I'm getting beside myself. I'm kind of this is beyond where we need to be. It says our t is from 0 to 10. So let's plot 0 to 10 there. Okay, and let's see. So we've got x. We've plotted the equation. We've got the y equals, right? We've got the specified parameter interval. We've done that. That's just everything we've just plugged in. And we've got the standard viewing window. So if we press graph, it should be exactly what we want. And that looks really weird, but that's exactly what we want. our graph should look something like, the answer should be something like this. Just looks like that, or whatever. I can't draw as well as the grapher can draw, but that's our answer. That's literally it. And we're done. So, fortunately, it ends on an easy one. Uh, we just plug it in and see what it says. Anyway, I hope this is helpful. If you have any further questions, let me know. I'm here to help however you'd like me to, and I really hope that you get something out of this. I think it's just really fun doing these things and finding the answers to these problems. I think it's just really cool. Um, and and again, I say this a lot, but I think the more I do these problems and the more I solve them and the more we solve them together, the more I see the beauty and the complexity of God and all of these things and how good He is for making something so systematic and something so orderly. Um, when we're pressured and we have to do all these things, we have to work really hard to get all this done, and we gotta get all the things done. We gotta get it right, and we gotta get a good grade and all that, and that's important and that's good. But I hope we don't miss the beauty of, and the fun of just like seeing, exploring these new concepts and these ideas about the way numbers can work and the way we can change and manipulate numbers to do really cool things. I mean, we just found a new way to think about time and a way to understand and structure time so we can see the movement. And I think that I love to think about that and just look at the implications of what does that mean for us? How does that change us as people? How does that change the way I see the numbers? Um, and how does that change what I can do in the world and how in the ways I can better it and the ways I can do really cool things for God's glory with it. I don't know. I'd like to think about what parametric equations can do for us. Maybe to help us visualize better the way the world works. Maybe with a good parametric equation, you can make an animation or a graphic that's really cool. And this literally is the fundamentals of animation. Is just looking at where something is at any given point in time. And so if you understand the parametric equations, you can understand the inner workings of how an animator works. And animators are super important to showing us the goodness and glory of God. So anyway, I don't mean to ramble on, and I know I'm very verbose, but I hope you have fun with this. I hope you kind of enjoy it, because I certainly do.